Hello, we continue with the topic of active filter, but now we move to the high pass filter. So hopefully at the end of this topic, you should be able to distinguish between the ideal and typical frequency response of high pass filter and the order of the filter, and then derive a transfer function, design the active high pass filter, and solve any related question regarding a high pass filter involving op-amp. Okay, now we look into the frequency response of high pass filter. So if you look over here at the pass band, you have a gain, meaning that after the cutoff frequency, you have a gain. But before the cutoff frequency, which is at the stop band, the gain is 0. So this is a brick wall frequency response, which is the ideal frequency response. But for the typical frequency response of high pass filter, there will be a transition from the stop to the pass band. There is a slope over here. Okay, and first we look into the passive high pass filter, which consists of capacitor and resistor. If you look closely at this circuit, it is opposite of a low pass filter. The position of C and R is interchanged. Okay, you have R at the output, but for the low pass, it is capacitor over here. This is passive because it is just the passive element C and R. So the output taken at R will be using a voltage divider, is your Vin multiplied with the resistor over here, Vi multiplied with R, divided by the total impedance, which is the impedance of the capacitor plus the resistor over here. And Zc is simply 1 over j omega C. Plug in into the equation and simplify it. Okay, so your VO is Vi multiplied with R over R plus 1 over j omega C. And if you simplify, you'll get the transfer function. H is the ratio of VO over Vin. It will be 1 over 1 plus 1 over j omega RC. So this is the transfer function for high pass filter. Okay, again, how do we analyze this transfer function? Substitute W or omega over here with a very high frequency first. Okay, so this term will be very large. 1 divided by a very large value. This part is 0. So your gain will be 1. Okay, and if you substitute into the equation omega to be 0 at very low frequency, 1 divided by 0, so you have a very large value plus 1. Okay, so what you get is this 1 divided by 1 plus infinity, so it goes to 0. So meaning that at a very low frequency, there is no gain. Okay, so it is the behavior of high pass filter. And if you plot just the curve, okay, at 0, there is no gain, but at a very high frequency, the gain is maximum, which is 1. So this is passive filter, the maximum gain is 1. At the cutoff frequency or corner frequency, it will be a drop by 30% or at 0.7071 of the maximum. So that will be your cutoff frequency, and the formula is given as 1 over 2 pi RC. Later we look on how to get this. Okay, so at the stop band to the pass band, you have a slope of positive 20 dB per decade. Okay, so this is in dB, 0 dB, 20 log of 1, minus 3 over here, this is your cutoff. So this is your bandwidth or the pass band. So this is the transition band. Okay, and there is a phase difference between VO and VI. At a very low frequency, the difference is 90 degree. At the cutoff is 45 degree, but at a very high frequency, there is no phase difference between VO and VI. It is in phase. Okay, it is the simple explanation as the low pass. Okay, why there is a phase shift. Now we look into the active high pass filter. So the difference is just now we just have C and R over here, but now we add the amplifier over here. So it becomes a active high pass filter. Okay, so this one is the filter, this is the amplification, which is the amplifier. Okay, and we can get the transfer function for the whole circuit by looking at the filter circuit first. Okay, from this you can get the transfer function, and this will give you also the cutoff frequency. The CNR will determine the cutoff frequency. So from this node is coming to the amplifier just now. It is V plus or V minus. So V plus and V minus is the voltage across R. So VI multiplied with R over the total impedance in the circuit. So VI over VI, V in will be 1 over 1 plus 1 over j omega RC. Okay, so this is the transfer function for the filter. And then from the denominator over here, again, you can determine the cutoff frequency. So it will be 1 over 2 pi RC. So this value of R and C will determine the cutoff frequency. And then for the amplifier, it is a non-inverting amplifier, RF over R1 plus 1, since it is the input coming to the positive terminal. So you will have a gain of this. Okay, VO over V plus will be 1 plus RF over R1. Okay, just now, the gain, this is coming from the filter just now. So the overall transfer function will be simply A divided by 1 plus 1 over j omega RC. So you have the amplification factor over here. If you compare to the passive, this is not A but 1. Okay. And this is the frequency response just now I have shown previously. 0, 20 dB per decade. It is increasing with the increasing of frequency, and this is how it looks if you draw it in the log scale graph. Okay. So that one is the high pass filter with non-inverting amplifier. Now we move on to a high pass filter, but it is inverting amplifier. If you look over here, V in is coming to the negative terminal, and this circuit is actually a differentiator. Okay, you have learned about differentiator in chapter 1. So now we look into this differentiator as a high pass filter. Okay. Again, since there is a capacitor, if you look at this is the reactance of the capacitor. If we put a F in this equation, suppose the F is infinity. Okay, 1 divided by infinity, your reactance will be 0. So meaning that it is a short circuit over here. If it is a short circuit over here, this circuit R2 over R1, this is VI, this is actually inverting amplifier. So if it is inverting amplifier, the gain will be minus R2 over R1. Okay. And then from the impedance of the capacitor just now we put the value of F to be 0. 1 divided by 0, it goes to infinity. This means that the capacitor over here have a very large reactance. So it will act as an open circuit. When the circuit is open, there is no signal coming from the V in over here to the output. Since this is an open circuit, the gain will be 0. Okay. So it is the characteristic of a high pass filter, because if you plot it, okay, at 0, this is the 0 just now, there is no gain, it is 0. But previously, at a very high frequency, you have a gain of minus R2 or R1. So in between, there is an increasing, okay, 20 dB per decade. As you increase the frequency, the gain will be increased up to the maximum minus R2 over R1. So after the cutoff, you have a gain. Before over here, okay, it is the transition. So this is the behavior of high pass filter. Only high frequency greater than FL can pass through the circuit. Okay. This is to find the transfer function. So for this, VI minus 0 is actually the current flowing from this node to this node. You have R1 and C in series. So R1 plus 1 over j omega C. And it is equal to the current over here, which is through the R2, flowing from this node to VO. So that's why it is 0 minus VO over the resistance over here, R2. Simplify this equation. And this one is 0 because this is grounded. Okay. And you get the VO over VI, which is simply minus R2 over R1 divided by 1 plus 1 over j omega R1C. So the transfer function A, which is the ratio of VO over VI over here, is minus R2 over R1 over 1 plus 1 over J omega RC. So this is the transfer function, the maximum gain. Okay, there is a negative sign in the equation, meaning that there is a phase difference between VO and VI. And from the transfer function, if you analyze it, okay, put it omega to be 0. So what you'll get, the gain will be 0. But if omega over here is infinity, you'll get the maximum gain minus R2 over R1. Okay, so from the transfer function, we can determine the cutoff frequency of using the denominator over here, equate the real part with imaginary. Okay, so 1 equals 1 over omega R1C, and from there you get the cutoff frequency in radian per second to be 1 over R1 over C, or in Hertz 1 over 2 pi R1 SC. The easier way to remember the cutoff is determined with the resistor and capacitor in series. Okay, thank you.